Good afternoon, everyone. My name is Andy Katz. I'm a product manager at AWS. I'm joined today by Scott Trillia from Yelp, his tech lead there. We're going to talk to you today about step functions. But first, I would like to start with a short survey. First question, how many of you have already tried step functions today? Okay, maybe 15% of you. How many built an application having tried step functions? So more than one of the demos, even fewer. Okay, my goal by the end of today is that all of you have tried step functions, built your first workflow, run it successfully, and are inspired to do more. So today we're going to talk about the benefits of using orchestration in a distributed environment. A little bit about how step functions works. So we're not going to go too deep into the service, but give you enough to get context. And we're going to talk a lot about what customers have done using step functions to give you some ideas about what you can do in your applications. So we're going to begin with a story. I know it's crazy business week, and you want to make a reservation at a restaurant. You have on your phone an app, let's say maybe one from Yelp. You take out your phone, and you search for restaurants. And you may filter by those that take reservations and that have tables available for the time you want to eat. You pick a restaurant, maybe a vegan steakhouse, and then you select a time. And maybe the app asks you for how many people, prompts you for a phone number, maybe an email address, and you have a reservation. And voila, you've completed a workflow. So how do you build this in a distributed environment like AWS? Well, workflows always describe a series of steps. So let's take a look at just two steps, step A, step B. And you want step A to happen before step B. For example, you may need to pick a time before the application checks for restaurants that have open tables during that time. So your first choice is whether are you building this as a monolithic application and putting both steps in the same instance or the same container, or whether you're going to build it as a distributed application where you have different instances and different containers taking care of different tasks in your application. As you can imagine, we recommend a distributed application for availability at scale. Now, by separating these steps and connecting them, for example, with a queue, you can scale each horizontally independently of each other. So if the first step is handling customers, and it's a busy week like this week in Las Vegas, you can scale out step A. On the other hand, as Las Vegas grows and people add more restaurants, you can scale out to handle the more tables that your app requires to support. But suppose the logic is different. Suppose your app only requires a phone number or an email address. Or maybe you want to reserve the table and collect the customer contact information simultaneously. So do things either or in parallel. You can do this with queues, but now you have many points of contact to maintain. What if you started accepting fingerprint scans as part of the customer identification in your app? As your workflow changes, you have multiple points to update and a couple components to maintain. And now the workflow logic is intermingled with your application logic. At all these points of change, you're also going to find you have repetitive patterns. You may want to retry when a task fails. Do it again. You may want to run things in a sequence. We talked about do A, then B. You may want to select what task follows based on the outcome of the first task. So do B or C depending on what A found out, like tables available, tables not available. 7 p.m. is not around, but 7:30 is. You may want to run tasks in parallel, contact the customer and the restaurant at the same time. You may want try, catch, finally pattern. So try this, if successful, great. If not, do something else. Now, certainly you can maintain all this code along with your business logic, or you could choose to separate the things that orchestrate your workflow from the business logic that makes your application unique. We call this a separation of concerns. So instead of each element of your application having a combination of business logic and workflow logic, separate the two. You can make your tasks stateless and focus them on doing one thing well, single deterministic task. And then you keep track of the state of your workflow in a separate layer of your application. This layer takes care of the overhead of retry, timeouts, error handling, and conditional branches and parallel steps. And it doesn't need to work exclusively with your compute resources. You can also leverage AWS resources as your task list workers. So how do you do this? Step functions. AWS Step Functions is designed to make it easy to coordinate components of distributed applications, and we do this in the form of visual workflows. The point of using step functions is to make your life easier. We want to make you more productive. As a fully managed service, we take care of the workflow infrastructure for you. This allows you to spend more time thinking about and innovating the business logic that makes your application unique, and your applications are easier to operate and maintain. Step Functions records an event log of every workflow execution, so you can review it all in one place, all the events in sequence in one location. You can scale from a single execution to hundreds of thousands of concurrent executions, especially when you use with other resources such as AWS Lambda, Amazon S3, and Amazon DynamoDB. With Step Functions, you only pay for what you use when you use it. It scales with your application. It supports automatic error handling for retries and graceful exits, and operates at scale without you needing to configure or manage any of that underlying workflow infrastructure, fully managed by us. Now, last year at reInvent, we launched Step Functions, and we took a selfie with the audience. If you will indulge me, we will begin a tradition and do it again. I'm going to ask everybody to smile and wave for the camera. Hello? All right, thank you. Now, why do we do this? Well, suppose we're building a photo sharing site. What might we do with the picture I just took? We could upload and we convert it into different formats. We could extract and transform information in that photograph, and we might do this for many, many photos. So this is an example of a photo processing workflow. In this case, you take a photo, upload it, and then in parallel, make a thumbnail and use Amazon recognition to identify features of the photo. Hopefully in this case, it finds people, not necessarily mountains or snow today. And you might then do this for many, many photos. The flowchart on the right is an actual step functions graph. Each stage of this workflow is represented by a state, and you have different types of states. You can see task states, which are the workhorse. They do work. Choice states add branching logic. If it's the wrong kind of image, you can go to a fail state to exit with an error condition of your choosing. And then you have parallel states to do work that's decoupled and can be run in parallel for efficiency. Now, you may recognize this diagram as a finite state machine. Workflows and step functions are defined as finite state machines. Now, you declare workflows in JSON using what we call Amazon States language. It's declarative, and this is what that previous workflow looks like in ASL. You can see that it starts at the first state, which in this case was extract image metadata, and each state is connected by a field that says next. So literally, state, next, next. In each state, you can put try-mounts, retry, and catch clauses. So you can see, whoops, excuse me, wrong button. That probably doesn't work. You can see a catch statement, an array of catch elements. So if you get certain kinds of errors, you can go to different parts of your workflow. You can also see retry policy that says if you get an error, try the state again. You can put in exponential backoffs to back off and retry, and you can do this state by state in your workflow. This makes the code contain your business logic in your task states, whether they be Lambda functions, containers, or EC2 instances, or even on-prem servers, much simpler to develop and maintain. Your workflow is going to have a lot of task states. Step function supports two types, Lambda tasks and activity tasks. Lambda task states, you see on the bottom here, push work to a Lambda function for you. When a step function state machine execution lands in a Lambda task state, it will give the state data as input to a Lambda function. It will dispatch it automatically, synchronously to that function, and wait for the function to return a result. Takes that payload and then transitions to the next state in the state machine. Activity task states work with all kinds of compute, such as Amazon EC2 instances, ECS containers, even on-prem resources such as your laptop or mobile phone. However, they work differently. They're more like a queue. They hold on to each task until a compute resource comes along and calls in and says, hey, do you have any work for me of this type? And when Step Functions has a state machine looking for a worker to do that work, it says, yes, I do. Here you go. Call me back when you're done. And that's useful because an activity task state can remain open for up to 1 year. So very long-running jobs. Not necessarily computing for a whole year if you don't need to, but you can do things like human approval steps. But also some people are doing things in things like big data or bioinformatics where they do have compute jobs that last for hours. Step Functions can watch that work and retry upon failure. Now, when these workflows are running, you can monitor them from the console, from the AWS CLI, or through the Step Functions API. With the exception of the graph that you're seeing here, all the information that's in the console is also available from the CLI or from the API. So all three interfaces. You can retrieve general status information of your workflows. They'll give you the input you gave to a particular workflow execution in the form of the JSON key value pairs. It can give you the final output of your workflow execution. You can retrieve the event log, which we call internally the execution history, and see the inputs and outputs of that execution history state by state. And this is really, really useful when you need to debug when something unexpected occurs. So that's a brief background. You can certainly discover more by visiting the console. So let's talk now about what customers have built with Step Functions. We're going to talk about three broad use cases, or three broad categories of use cases. First, automating daily, weekly, or monthly tasks. We're talking about coordinating components of distributed applications. And then we're talking about building, sometimes serverless, microservices, which themselves may be part of a bigger distributed application. And these are examples of some of the customers we're going to be talking about today, folks like yourselves. Some of you may even be in the room. So let's start with automation of daily, weekly, and monthly tasks. So our first example comes from Home24. Home24 is the market leader in online shopping for home and living products. They run their entire data analytics platform on AWS, and they analyze multiple data sources, including marketing data, social media data, search analytics, their internal ERP systems, and they bring all this data together into a single resource. They run this on AWS services like S3, Kinesis, Redshift, EMR, and DynamoDB to ingest, process, and analyze all this data. And they're importing, on a regular basis, about 50 gigabytes of data daily, and they need to turn it into a format that they can consume and query over. AWS Step Functions is used by the data team, which made it very, very easy for Home24 to build an ELT pipeline. And they lowered their costs 99% while doing it. But more importantly, their engineers are now more productive. They're able to easily integrate new data sources in a very short time, sometimes in about 5 days. So today they've got about 20 plus data sources they process in this Step Functions workflow, and they can add as they need. This made them more agile and more able to quickly develop pipelines to perform new transformations and new analytics. The platform is also more resilient and more reliable because it handles the API failures of all their different data sources, because Step Functions will automatically retry when the data is not available until it can get the data. The architecture looks like this. It's a data lake on S3. And they use the data lake to store both raw and refined data. So this is actually an ELT job. They extract, they load to S3, then they transform. Their workflow is completely serverless. So they actually chunk the data into bite-sized pieces that can be processed by a single Lambda function. So Lambda function is great and useful, but they can process only for 5 minutes at a time. So how do you deal with a bigger file? So in this case, you iterate. You do a chunk at a time. And so they start the workflow on a schedule using CloudWatch events, download the data from their 20 plus sources, break it up into chunks, and iterate over each chunk to refine it into the format that they can consume and build their second bucket on S3, which becomes the resource that they can use in a common data structure. Another example, this one, ETL, for subscription fulfillment by The Guardian. The Guardian is a British newspaper founded about 200 years ago with nearly 200,000 daily sales, and they have several workflows running on Step Functions. In this example, they're managing their home delivery list. Every morning, they need to give their home delivery fulfillment vendors a list of active subscribers. They need to know who's newly subscribed, who may have canceled a subscription, who's on vacation, doesn't want delivery, and that list needs to be updated every day for the delivery cycle. So before, they had a workflow that took place wholly within a Salesforce script. So there's custom Apex code, which did all the file generation, and it would occasionally blow up on them, and they would lose their subscription list. It also was selecting over a synchronized data set, and the sync wasn't reliable, so they had spotty accuracy in their information. And they had a limited number of people that knew how to manage this code. So they made a decision to rewrite the process and do it in a developer environment that they had more developers familiar with. They chose an ETL paradigm and a technical landscape that was familiar to most developers using AWS. And so they built a state machine, very simple, 4 steps. But now the fulfillment files are pre-generated, and they're very fast to download for their supplier. They use S3 versioning, which makes the process idempotent, so it's very easy for them to recover from failure. And they're actually able to make a rolling 5-day projection of deliveries that they can update every day and work around national holidays, which makes their accuracy delivery much greater. And so their workflow looks like this. Every morning, they need to give their suppliers this list of 5-day schedule. And they host their subscribers in Zora, which is a third-party SaaS platform. They have a schedule in CloudWatch events that every morning at 7:30 starts, kicks off the state machine, which goes and says to Quora, hey, get me the list of current subscribers that need delivery today, or tomorrow, or the next day. And then it waits. Waiting is cheap on Step Functions. And they wait for the Zora query to complete. They pull the data off Zora, put it on S3. They call another Lambda function that transforms it into a format they can load onto Salesforce for consumption by their delivery service. Supplier logs in, selects the date range they're interested in, pulls down 1 to 5 files of the forecast, and they're good to go for that day. Another example of a regular workflow. This is a weekly task, perhaps. Business continuity, as you know, is important, particularly when you have a mission-critical workload on AWS. And a lot of things are backed by an EBS volume. And a good practice is to back up that EBS volume on a regular basis. Take snapshots, store them in your region, store them in a disaster recovery region. This is a way to automate that. And how do you do it without servers? Step functions. This is an example with 2 serverless workflows, one in your primary region, one in your disaster recovery region. Each workflow looks for a CloudWatch event which says, hey, an EBS snapshot volume was created. That kicks off a workflow that does 4 things. It says there's a new snapshot, tag it, counts how many there are, starts the disaster recovery copy to the DR region, and then counts what's there and says anything that's out of date, delete it. So it's a way of keeping a steady state number of snapshots that are all fresh and cleans out and curates stale snapshots. And the second state machine that's in your disaster recovery region does the same thing. When the copy over the DR region is complete, CloudWatch Events kicks off a second state machine, tags it, counts how many are there, deletes the old state machines, and then both of them send a message on SNS to say, we're done and you're up to date. So it's a nice way to automate a daily task or a weekly task in this case. Here's an example of simplifying a monthly task. So suppose you're managing a website. As a website owner, you want to update your production website without all the changes, with all the changes you've made in a reliable and fast way, without having necessarily to delete the entire bucket and copy over everything you've changed in the website. So this is a way to do a differential. This workflow does 3 things. First, it copies all files from a source bucket into a destination bucket, but doesn't move objects that are already present in the destination bucket for efficiency, so it only copies what's new. Then it looks in the destination bucket and says anything in this destination bucket that's not present in the source bucket, it deletes. And then it just keeps track of all these objects, regardless of how many are in each bucket, so it synchronizes the 2 buckets. This is a way of actually moving from a dev bucket to a prod bucket in a website live quickly. This is an example of a use case we have posted on GitHub, so if you want to try it yourself, feel free to try. Just caveat emptor. Deletions on S3 are pretty much a one-way door, so be careful with what you connect to the state machine. And now here's an example of a task you never want to run. This workflow automates the response to an accidental exposure of your IAM keys. So AWS Health is a service that monitors things like GitHub to see if somebody's accidentally put your IAM keys. And if it has, it sends an event. In this case, it triggers a workflow that does three things. First, it goes in and quickly goes and says, delete that key pair, it's been exposed, it's compromised. Second, it goes to CloudTrail and says, have there been any recent API calls or any suspicious activity associated with that key pair? And then finally, gathers that information, sends it on to security saying, there was a breach, here's the CloudTrail, go take a look, and it makes security's review faster and easier. But you'll see it also has in it a catch statement which says, if for any reason it has trouble deleting that key pair, maybe somebody else detected it and deleted it themselves, it still notifies security and says, I found something anomalous. So you're guaranteed that security gets notified one way or other, either with full information or the partial information that is available. Again, you don't want to run this, but it's there and runs when you need it. So these are examples of daily, weekly, and monthly tasks that you can automate. And in some cases, these are workloads that you can imagine running at scale, and in other cases, they were simple enough to consider replacing a shell script for greater resilience. Now we'll look at some things that are a bit bigger. Distributed applications built on step functions. We'll start with drones. Drones are interesting. SkyCatch provides drone data to industrial enterprises. They do machine-to-machine automation, to do inspection of building sites, to provide their partners metrics on what's going on during construction of the building. They have a scalable data processing platform that's cloud-based, proprietary photo processing, and they can custom tune that processing for the specific requirements of their customers. And they have machine learning algorithms that do things like count trees, remove objects, identify targets, and this all runs in the cloud. They have several state machines, but one that's interesting is they use the state machine to pick the resource they want to use to compute the job. And they save 60% on their costs and improve their SLAs for their customers at the same time. Their state machine chooses between a spot EC2 instance and an on-demand instance, and they can give up on the spot auction if they're running out of time to complete the job. So they first go into a first state, which says, how big is this job, when is it due? And if there's enough time, go to a spot auction. And if the spot auction doesn't yield an instance in time, they can default over to an on-demand instance to complete the job on time. But by managing their compute resources in this way, they pick the right instance at the right time, for the right job. They also found that by using state machines in their workflows, they can simplify several stages of their operation. They simplified error analysis, because not every drone photo is perfect. Sometimes the drone takes a picture of the sky, and that can interfere with the workflow. This allows them to resume processing images with a consistent protocol whenever they find an error in the data set that they're processing. In this case, the architecture is pretty simple. You have a Lambda function that evaluates the job. It makes a choice state. It says, do I go for the on-demand instance or do I go for the spot auction? Once I've got the instance up and running, it runs an image processing workflow, which is another step function state machine. And when it's all done, they can take down the machine. And they monitor these things using, they can use an asynchronous polling loop. We call it job status poller in the templates on step functions to watch asynchronous tasks that are running in things like EC2. Now for a second example, we've invited a customer to tell you about it themselves. It's fine if I tell you stories, it's better for me to hear it from a customer. So Scott Trillia is a tech lead at Yelp. He's here to share their experiences building distributed applications with AWS Step Functions. Scott?
All right, thanks Andy. I'm here to talk a little bit about how Yelp uses step functions. So to do that, I'm going to be introducing you to the concept of subscription billing as it exists at Yelp. And in particular, we're going to be talking about this use case where you have an old code base, something that maybe doesn't look quite like you want it to, something where you can think of some rough edges that have emerged over the course of, say, the last 10 years. And the reality is that all of our older code bases tend toward something like this, right? They tend toward spaghetti. And we essentially have this problem where we want to fix that. We want to take this code that isn't quite how we think it should be to a better place, maybe use some of the cool concepts that you've been hearing about here at reInvent, but we need to do so safely and effectively. So what we're going to talk about is the monthly invoicing process for advertising accounts at Yelp. And this is a really business-critical process. It works over about over 100,000 accounts as of this year. And it's something that's scaled up over a long time, and it's changed over a long time, but it's still responsible for the majority of the revenue that Yelp collects. So if I'm going to go in and make a large architectural change, I need to have a lot of confidence that that change is not going to break anything. So I can contextualize this process within a much longer job. Out to the left and the right of this diagram is a nightly job. It runs for, these days, around 7 hours roughly, and it does a lot of stuff. It's very important. The responsibilities of that long process are not solely according to my team. But within it, right in the middle, we have these 3 important steps. And these correspond to the collection of money from advertisers. So first, we go over all of the accounts that we're discussing, over 100,000 of them, and we're essentially trying to figure out what does each advertiser owe to us. That's the bill account step. And then after that, we're going to make invoices and we're going to collect money from those accounts. But as we were scaling this up, we hit a complex problem. We started to feel the pain of an old process running on old code that maybe we didn't understand like we wanted to. That bill all accounts step is running over a lot of different accounts. And if one of them, maybe you're 25% of the way through the workload, fails, you would stop the whole process. It would halt, it would page on call, maybe nice and early, something like 5 a.m., and it would tell us something kind of uninformative. It would say, hey, Scott, it's 5 a.m., wake up, please. And then it would tell me something went wrong with the billing of all accounts, right? An error occurred, we're 25% of the way through, everybody's waiting for us to finish the other 75% of the accounts, good luck. And that was essentially the job we gave to our on-call engineers. And that's a pretty rough situation to be in. So we wanted to make it better, we wanted to make it more resilient, we wanted to make it more observable and understandable. Now, we zoomed in and we said we're just going to target this first section because we think we can do a better job if we focus a little bit. But it turns out that focusing on just the billing of accounts, just deciding what people owe, wasn't enough to make this an easy problem. We still couldn't observe the tasks that we had to do here. We still didn't understand what would fail or why. And it was older code. It was tangled, and it was still complex. So luckily, we could use step functions to make that all possible. Now, we've heard a lot of cool concepts. If you were at the ARIA yesterday, you were exposed to a lot of serverless concepts, things like API Gateway, things like Amazon Lambda. And these are really cool tools, and we thought maybe they'd be relevant for us. But they weren't quite things that we felt we could apply right away. No good API existed for this code, so it wasn't going to work to put it behind API Gateway. And as far as the complexity and the granularity of the functions, nothing was really small enough that it felt like Lambda was really relevant for us. We're not factored into these small, nice pieces. So we're left in a spot where we know we want to maybe make progress in this direction, but we can't use these tools directly. Now, our old code looked roughly something like this. This is the process for billing every account that we need to go through. We would take this large set of accounts, and we break it into chunks. We had a homegrown parallelism framework that allowed us to do some amount of concurrency within each chunk, so we weren't literally serially working through 100,000 accounts. But then the real meat of it, the logic that we cared about, was this bill account method. And this is where we decided how much to bill, whether someone had used ads this month or not, and concerns like that. So that was where all the logic was. And this is where we started. Now, our first choice was, how are we going to migrate this onto step functions at all? So we went ahead and decided, and this luckily was something that felt pretty correct and pretty easy, that the right granularity was to bill a single account in a single execution. And so our executions were going to basically map onto that bill account function that we just talked about. Now, we still had to trigger all of these, right? We had to have some sort of master process that was responsible for starting a lot of different executions. And so we kept just a very thin layer of code that was responsible for starting the executions as fast as possible. And we let Amazon go ahead and handle the concurrency, handle the monitoring of all these different executions in flight, and keep track of them for us. And something really nice that we saw right off the bat with that was we were able to start acting a little more like a service, right? We had a bunch of code sitting in a monolith. It was not nicely refactored behind some sort of API. But step functions, when we were starting these executions, required data. And we were able to start acting as if we were communicating with a service far in advance of actually having that built out. So we specified what it means to start billing for a single account. You have to supply an account ID and a date and something like that. And now our clients are nice and decoupled from the implementation of the workflow. So if we need to change how billing works for this particular execution, we can do that in the future, and our clients are none the wiser. But we had another problem. Andy talked earlier about the sort of distinction of how you do your tasks. You can either be pushing data into Lambdas, and we've already said that doesn't feel like it's immediately an option for us, or you can be pulling work with activity tasks. And so this was really nice for us. We could actually add just a little bit of glue code, just enough code to ask Amazon, should I bill an account? And after we were done, to be able to tell Amazon that it worked or it didn't work. And we were able to wrap the existing functionality we already had with minimal refactoring. Remember, the reason we weren't making this better in the first place is it was dangerous to change the code. So we don't want to change the functionality of bill account before we're ready to. But we can just wrap a little layer around the outside, and we can go ahead and have it integrated into our very, very simple workflow. So you might be wondering, Scott, you've described a workflow here with a single activity task in it. That doesn't sound super compelling. I don't understand why this is even valuable yet. And it turned out that there were a few things we got right off the bat just by integrating with step functions. The first of those was a real boost in concurrency. So I talked earlier that we already had some in-house method of parallelizing billing across all these accounts. And we were now relying on step functions to manage the parallel billing of all these different accounts. And what we found was that that parallelism factor was really easy to change. So we can either kick off more simultaneous executions, or we can tune that down and maybe even kick them off in serial at the extreme. But maybe more importantly for us, it actually offered significant speedups. So this is what might look like a fairly boring graph, but it's actually really exciting to us. We're plotting on the x-axis time, so about the 3-hour period where we're doing all these executions. And on the y-axis, we're plotting how many executions we are starting over that time. And what we saw with step functions was basically it soaked up these executions as fast as we were able to send them. And this is true over the entire 3-hour period of the batch process. Now, our old process wanted to do the same thing, but had some degradation in parallelism over time, and so this was actually a big boost in the overall efficiency of billing all these 100,000 plus accounts. And we've actually written up some of this into a blog post. If you look on Yelp's engineering blog or Google Yelp Step Functions, you can see a little more detail on how it worked before and why this was a big improvement. But it wasn't just that performance that we got from this, right? That wasn't the only benefit. We saw a lot of improvements around observability. And if you remember back to the original problem, the reason this code was dangerous for us to touch, this is actually a really central issue. Knowing whether or not I've successfully billed a single account, and in particular knowing whether or not I've successfully billed all of the accounts, is a really, really important problem, and it's going to get even more important for us to know as we start to change the logic and refactor the internals of this process. So we were able to explicitly handle success and failure modes, and we were able actually to represent those in the workflow itself. So this gives us a nice way to start to detangle all of the responsibilities of bill account. We're able to pull out things like retries, things like timeouts, things like what do you do in the success or the failure case, out of that single mega function and into these other activity tasks or the step functions workflow itself. And maybe most importantly, we now have failure at the granularity of a single account. If we remember back to that on-call engineer's problem, they were woken up at 5 a.m., told that the entirety of the process had failed, and it was currently making no progress on any accounts, right? And that might have been because a single account had an issue. That might have been because 10% of accounts were having issues. But the point was everything stopped. The whole world stopped while that on-call engineer woke up, diagnosed a pretty vague problem, and tried to restart the process successfully. So when we break the granularity of failure down to a single execution, we can have 5 or 10 accounts that are having problems today. They'll have really clear feedback signals to us. We can tell that something went wrong. And the other 99% of the accounts that are working just fine carry on in parallel. So decoupling those two was a big win for us. And I talked a little bit about timeouts. We didn't have a concept of timeouts in the original system. It was happy to chug along and keep working for as long as we let it. This led to a really painful postmortem sometime last year where we had the billing process get way, way, way slower for about 10% of our accounts that we were doing billing for. And the way that we figured this out was not any timely feedback, hey, your code is getting slow. We figured it out at 2 p.m. when the job was supposed to have been done for hours, and it turns out it was way at the start of its workload. So we wanted to speed up those feedback cycles. We wanted to be told immediately when we were having problems with things running slowly or not completing, and we were able to put that into place with the timeouts that Step Functions supports. They're very flexible. We can say that an entire activity might be really slow for a large account, like 20 minutes, and we can still dial in those heartbeats and say, if I don't check in with you regularly every minute, something has gone horribly wrong. Please treat it as a failure. And if we want to retry on these, we can build that into the workflow, and if we want to hard fail, we can choose to do that too. And we've talked a lot about observability and improvements in the reliability of the process. And this is where it really starts to pay for itself. We've gotten onto Amazon Step Functions. We've been able to start using these very simplistic workflows. And now we can start making the real refactorings that we had originally wanted to do safely and with confidence. So we can say that, hey, that bill account step, it looked a little large. It still had a lot of functionality packed into it. Let's break out different steps for bookkeeping for the different types of products that Yelp sells. And we can do this in parallel, which is something that Step Functions supports. And we can maybe run this side by side with the old state machine and gain confidence that it's working correctly, that it's working successfully before we roll it out all the way. And this is something that wouldn't have been possible with the old system. I couldn't have told you whether or not things were working reliably or correctly until I tried it one day. And this gives us a much more realistic method to roll these concepts out and to make more refactoring improvements down the line. So I want to kind of take a step back and talk about overall the benefits that we've seen. Now, I don't know about all of you. I don't know where the code that you work with is on this spectrum from kind of a monolithic world to services or microservices, or even all the way over to functions like Lambdas. But I can say for myself, my code, it tends more toward the monolithic side. It's somewhere in between monolithic and microservices. And so having an execution model, having a tool like Step Functions that can flexibly support me where my code is at and give me the sort of power and leverage I want to maybe move more in a microservices direction is really, really valuable. And we saw that it can support us all the way at the fully monolithic side and incrementally as we move more and more distributed. And the other side of this is it's really incrementally valuable to us. I can't go to my bosses or my product managers and propose a 6-month-long engineering trek with 4 engineers and have them sign off on that, right? I can't tell them, you're not going to see any value until 6 months are over, and then the whole thing's going to work great, I promise. Instead, we need something that's going to work right off the bat, give us value and benefits immediately, and then continue to deliver those over time as we make the system better and better. And right off the bat, we saw really great improvements in decoupling. Our clients were now unaware of how the workflow itself was processing. We saw really good benefits in terms of parallelism. We talked about the concurrency going up, the overall throughput of the process improving. And crucially, we saw those improvements in observability. So we were able to go from maybe not totally knowing if the system was working or not to quick feedback loops, very clear cycles, a system that we could incrementally improve and incrementally understand. And all that's really valuable. And that's kind of been Yelp's experience so far with Step Functions. It's a platform that's flexible. It can support our oldest applications with minimal modifications. But it's going to deliver those observability, those performance benefits right away. And then it's going to give us leverage, right? It's going to allow us to make the changes we want to make, change our architecture in the ways we think would be improved, and Step Functions is right there supporting us along the way. And before I hand it off back to Andy, I want to just walk through each of those steps in sequence, because I think it's really interesting to see the kind of iterative improvement and evolution of a workflow over time. So we started off with one very, very simple workflow. And essentially, the idea here was all I wanted to do was to start using step functions. I don't want to change code. We're just going to set it all right there in the middle as the sole step in a workflow. But we get the concurrency benefits, and we get the observability. And after that, we can start to instrument it for better observability. We can start to decouple error handling, logging, metrics, failure modes into their own tasks, and that can give us even more confidence going forward. As we start to build the kind of system that we think ought to actually exist here, we can break down larger functions into smaller substeps. We can run them in parallel for efficiency purposes. And all of this is being done with the kind of observability and confidence that we gain from using step functions in the first place. And then maybe if at some point we feel ready for it, we think it's right for our use cases, we can selectively move some or all of these tasks over to a push model with AWS Lambda. And having that be ready for us when we decide it's correct, and having step functions work with us over the whole process has been super valuable. So with that, thanks for listening, and I'll hand it back off to Andy.
So that's pretty cool. A monolith transformed into a distributed workflow simply by adding step functions. Again, I think that's pretty neat. And again, that blog, if you want to search for it, if you just search step functions Yelp or Yelp step functions, it will come up. It's brand spanking new. So finally, I want to share with you the third use case. Some examples of customers building microservices using step functions to back behind the API. So first is an example from Ellie Mae. Ellie Mae is a cloud-based platform provider for the mortgage and finance industry that processes almost 40% of US mortgages every year. They created an internal self-service API to run performance tests on their application development and managed infrastructure in order to reduce costs. They created something they call POP, the Performance Orchestration Platform, to reduce costs. They saved nearly $10,000 a month doing so. And what's their approach is step functions. This is going to look similar to what you saw a little bit with SkyCatch, is they calculate and set the number of tasks they want to run on ECS. So now they're using containers. And they deploy these containers, and then one of the containers actually goes and listens to step functions for a task, which then represents the job they want to test, deploys the infrastructure, runs the test, tears down the infrastructure, reports the result. So it's actually, in some ways, a state machine pulling itself up by the bootstraps because it's going to deploy in the form of containers the activity workers that it's going to use downstream in the execution. Well, the team had some really interesting outcomes from this. They told us that in the course of building this project, they had fantastic sprint demos. They had a lot of fun week over week showing what they had accomplished. They actually wrote less code. They obviously saved money in their infrastructure, and they now have an app that is CI/CD ready for automating test results. They learned a lot of lessons along the way. Their recommendation, our recommendation, break down tasks into deterministic steps. If you use Lambda, Lambda can be very easy to debug, especially if there's simple single task functions. When you have large documents to pass through your state machine, store those in S3, pass the object key through the state machine. That's a way to manage big documents. We want to move megabytes and gigabytes through a state machine. You saw Home24 doing something like that as well. And finally, use activity tasks wherever you have something that runs for a very long period of time. This is what their architecture looks like. It's a little bit elaborate, but essentially the job they want to run, they put on S3. They add the job to a Dynamo table. That Dynamo table is picked up on a schedule from CloudWatch events, takes that input from DynamoDB, runs the workflow that calls CloudFormation to scale up an ECS cluster, validates that new infrastructure, runs the test, publishes the results, user gets the results back through the API, and they take down the infrastructure. So it's ephemeral testing frameworks at scale. Another example. This one comes from OutSystems. Now, OutSystems, if you go online and look at our talk on step functions last year, presented on a very interesting use case. They're aggregating alarms, so their engineers weren't waking up in the middle of the night. This year, OutSystems shared something new. They built a microservice that, in this case, manages migrating off of one RDS instance into another. OutSystems is a company that provides a low-code platform for development of mobile applications. And they had this challenge of their customers were outgrowing their RDS instances. They have a single-tenant platform, everybody gets an RDS instance, and they had to pick a size that would fit everybody. But eventually, some customers were outgrowing, so they had to over-provision everybody to handle the small number of people that were growing. So they used step functions to address the challenge. They actually built a workflow that would decommission an old RDS instance, create a new RDS instance with a bigger volume, and move the data over. And to do so, they took advantage of a capability on RDS that allows you to back up your database onto S3 and then restore it. So in this case, they built, it's very hard to see, but that's a state machine that goes through a series of steps that takes down that RDS instance, moves the data to S3, deploys a new instance with a bigger volume, and then restores. And by doing so, they were able to reduce their storage costs 60% by moving from a base instance of a terabyte down to 400 gigabytes, and then scaling as their customers needed. This is what their reference architecture looks like. Again, API gateway calls, puts the task into Dynamo and starts a state machine. First, they check that they have all the requirements, and they wait for an approval to get going. They then cut off network access to the database instance except for a single IP address, so they put a bottleneck. They back up the existing database onto S3. They create a new database instance with that larger storage volume. They start the backup. They wait for the backup and restore to complete. They then configure some things that are specific to their architecture. They swap the names. They restore network access to the new instance, and they tear down the old instance. And so, you know, hands-free from the operator, done through an API call. So these customer use cases, we've gone through 6, should give you an idea of the wide range of ways you can use step functions, again, to increase your productivity, your agility, and your resilience at scale. And whether you're replacing a brittle shell script or running a huge workflow like Scott does at Yelp, or other customers, step functions offers you an easy and fun way to add resilience to your applications. And we have more sessions this week, including this one that will be online soon. So we're overlapping right now with a chalk talk, but we have coming up a workshop tomorrow. And for those who want to do a deep dive into serverless architectures on step functions, we have one on Thursday, State Machines in the Wild, with even more customer examples there. Also, we'll be at the serverless kiosk in the expo, so come feel free to talk to us. Understand that not just serverless, but we also speak containers and instances and on-prem servers, so bring anything and all questions to us. But also you can get started by visiting our URL, stepfunction/reinvent, for blogs, reference architectures, tutorials to get started today. What I'll encourage you to do, again, I told you my goal at the beginning was to get everybody in this room to build a state machine, and I'd ask of you to build a state machine this week. There are 3 if you go to the console. The easiest one is this canonical Hello World. You saw Scott used it to build out microservices at Yelp. There are 3 flavors. The first one you can build in 5 minutes, actually in 2 minutes. Use a pass state. You can also build it with a Lambda function as a Lambda Hello World, or you can build it with an activity task state. All 3 are in our developer guide with step-by-step tutorials, and you can start in the console and build it easily, and all will fit in the free tier. When you get done playing with that, where you can explore retry and catch statements, then maybe go to the second one, which is task timer, where you introduce a wait state and wait for some period of time, and then call a Lambda function that puts a message on an SNS topic, send yourself an email. That one takes about 5 minutes to put together and starts to expose you to some of the power of step functions to do long-running tasks with Lambda functions. And then finally, if you want something more advanced and interesting, the job status poller lets you manage a job on AWS Batch. And asynchronously calls Batch, sends a job, and polls for that job status till it's complete, and then exits the workflow execution. Again, all 3 of these are in the developer guide. We have step-by-step tutorials, and all 3, in terms of use of step functions, use of Lambda, will fit in the free tier. You can run a couple hundred executions and stay well within the free tier, so feel free to try with no fear of incurring a bill. And then finally, tell us what you built. Hashtag step functions. Please post what you built. Show us a picture of your state machine. Tell us what you liked. and we'll keep an eye on it. And who knows, if somebody posts something really interesting, we may be reaching out to you and inviting you to be here with us next year on stage. We look forward to hearing from you. Thank you for your time. Scott and I will be in the corner here, happy to answer any and all questions you may have for the next few minutes. Thanks again.